Swayam Prabha. Digital India. Educated India.
Welcome back. I hope you are a little refreshed now. So we move on. Of course, I don't want to talk more about thermodynamical aspect, as Professor has already pointed out. I talked about an electrical interface. When I talked about the electrical interface, if you have to structurally envisage it, how does it look? It looks something like this. I have a metal surface, and a metal surface in vacuum is always charged. It's not going to be electrically neutral. But now when I assume in the real conditions, which is apart from ideality, that I have electrolyte, the electrolyte is again a charged species which contains an anion and a cation. When charges are present, here on the surface, the metal has certain willingness to give electron based on its thermodynamical aspect. For example, zinc would like to willing to give more easier electrons than iron. That's what we know. Now when electron transfer happens, the surface which is at the metal and electrode interface, the electrode and the electrolyte interface is what we name it as electrified interface. And if you closely look at it, we talked about aqueous environment. That means basically you have water molecule, you have dissolved ions into it. The first thing is what happens with the fraction of a second is even much below a millisecond is first layer is the covering of the surface with water molecule. Water being bipolar or dipolar, you will have based on the surface charge of your metal, it aligns itself in a certain fashion. 70% of the electrode surface is immediately covered with a water molecule, which can also be a dielectric, giving an behavior similar to a capacitor. If the surface is negatively charged, the solution contains counter charges, which basically a cationic species, which again does not travel as it is solvated, it is now covered with water molecules, and they tend to come closer to the surface to a certain distance, which we call it as an electrical double layer. Now, if I look closely into it, I have a metal atom which has to move from this surface and getting into the solution as a metal ion. It has to overcome this electrical field which is generated, or the gradient, potential gradient which is generated at this interface. If I assume this is plus and this is minus, we know plus is always higher potential and minus is a lower potential. So there is a gradient at this electrical interface, which an ion species which has to move from the surface to the electrolyte, or an ionic species from electrolyte to the surface of the metal has to come across. This energy is what we say it as related to delta G as minus NFE. That other words, we say the energy required to move a charge of NF reversibly through this potential difference. And if I ask you a recap question, Professor has mentioned two concepts. One is single electrode and other is a mixed electrode. Can you recall what is single electrode? Material act as an anode and cathode. That's right. Little more specific. Very clearly, the word was very clearly written, single electrode, when he explained the EMF series, or when he said if I have a metal which is dipped in its own ion of 1 molar concentration or activity at a temperature of 298 Kelvin or 25 degrees centigrade, and the gases involved in are in 1 atmosphere, it is what he defined as a standard state, and at that standard state it gives me a potential which can be measured using a reference electrode, and he said that reference electrode is a standard hydrogen electrode. So what is that? That is a single electrode. If I assume there is a metal, an electronic medium inserted into an ionic medium, and now I am fixing the concentration or the activity of these species. So whatever happens at this interface, basically metal will become metal ion and metal ion can become a metal again. So it is a reversible process, and this is an example of a single electrode, a non-corroding system, and the reaction is at equilibrium and reversibility. It will give me a potential, and that potential is what we talk with respect to this, which can be correlated with your free energy change. So, no more in electrochemical or aqueous corrosion systems, we will talk about the feasibility of the reaction by the potential value. We need not remember the change in free energy value like minus 234.7 kilojoule per mole. That is not required. We will just say with respect to E alone, and that is sufficient. And this system which I say, where it is reversible non-corroding system, it is called single electrode. But now come to corrosion. Corrosion is a reversible process or irreversible? It is a irreversible process. Why do you say it is irreversible? Assume the same here. I have a metal. Now, here in the solution side, I am not fixing it with its own ion. I am not at the standard conditions. Let us say I have HCl as a solution. What will happen? Metal has the willingness to give the electron, it would give, but then that electron which are supposed to go for the metal ion to become metal is now stolen away by the H plus, which then on the surface of the metal you will have hydrogen gas evolved and the metal leaving the lattice and getting into the solution as metal ion. So, that way what happened? Two particular off reactions have become now kind of the electron which has to go for the metal ion to become metal, that reversibility is hindered. The H plus which is present is there as stolen away that electron producing H2 on the surface. So, this now is two independent reactions at two different conditions now becomes a single potential, and this is what we call it as mixed electrode. So, the corrosion process which we talk about is often irreversible in nature, and it is a mixed electrode, but not a single electrode. Okay. This has its own potential. That is the example what he said. If I take copper and zinc, which is nobler among these two, zinc and copper? Copper is nobler. So, if I make an electrochemical cell, I connect it with zinc and copper in an electrochemical cell, what will happen? Zinc would dissolve, zinc giving zinc 2 plus 2 electrons. The 2 electrons go to this surface, and the copper ion in the solution will pick up these 2 electrons, forming a copper. This is copper sulfate solution, and here is a zinc sulfate solution. Now, if I would have not connected them, if I would have maintained as an individual cell at standard conditions, they would have been a single electrode or an off cell. But now when I connected them, they become into a corrosion cell or a mixed cell, and it is irreversible, or it becomes a mixed electrode. So, you need to understand that when do I say as a non-corroding system or a single electrode, when do I say as a mixed electrode. This is very important to understand, especially the kinetic factor of the system. Now, this is actually the basis of ranking the elements in terms of its reactivity, which is nothing but your E is given in terms of delta G. So, you move from the top to the bottom, you are going to see that the more the nobler elements are arranged in the top and more activer elements are arranged in the bottom, right. So, if I can get a comparative behavior, I normally protect iron by coating it with zinc, that is called as galvanization. So, how does zinc prevent iron from corroding? Iron is saved. So, when zinc gets involved in the reaction, what happens? How is iron saved? Iron lattice cathode. So, basically if I consider an pipe, GI pipe, galvanized iron pipe exposed to an environment, I have shifted the anodic reaction of surface happening on the iron surface, I have shifted that to zinc, and the cathodic reaction is going to happen on the iron surface. So, the protection of zinc or galvanization of iron does not depend on the corrosion resistance of zinc, but the corrosion ability of the zinc is what used to prevent iron from corroding. That means, sacrificially zinc says, I can give the electrons on your behalf, you be the surface where the cathodic reaction happens. Therefore, he says cathodically protecting by a sacrificial anode. Now, if I consider between magnesium and zinc, what can you understand from here? Can I have magnesium as an anode for zinc? So, in this table, if you are below, that means you are increasingly active. If you are above, it is increasingly nobler. Now, the question comes is, what I am going to do with this? It is all element. I have no alloys into the structure here. I have no alloys. I don't talk about stainless steel. I am not talking about aluminum alloy, nor I am talking about nickel alloy or copper alloy systems. These are giving relatively placements of elements alone. And another point is, this potential is for what conditions? It is at fixed conditions of standard. That is basically at 1 molar of its own ion. It could be activity or concentration. We will come to that later. Second, we say that this is at room temperature of 298 Kelvin, and the partial pressure of gases involved are at 1 atmosphere. But in corrosion scenario, do we see this experience this environment, or do we see a different environment? So, take the case of the same when I have a copper rod dipped into a copper sulphate solution. If it is all standard, the value of this will be correct with respect to SHE, right. But now, if I change the concentration of copper sulphate, what happens? Will the potential remain the same? If I change the concentration of the copper, will the potential which I measured with respect to a standard hydrogen electrode, which will be at 0.34 or not? So, what does it say? The potential which is developed at the interface when a metal is dipped in an electrolyte, the potential is a function of the concentration of the species. Here in this case is the metal ion species, and also the temperature which is involved. This particular equation is called as Nernst equation, which says that your potential of an electrochemical interface is dependent on the concentration of the species involved and the temperature at which the process happens. So, you normally, for example, for hydrogen electrode, what is the electrochemical reaction for the hydrogen electrode? Can you say from the EMF series? Correct? Its E naught value is what? Is equal to 0 by IUPAC standard. Now, what will be if I change this? Let us say I am changing the H plus concentration or H plus amount. This will be given by an equation E equal to E naught minus RT by NF ln of the partial pressure of oxygen, it is a gas here, divided by the concentration of H plus in the solution. Now, if I assume that this is 1, okay, but you are changing this one, this equation will be 0 minus 0.059 into pH. I have taken R is the gas constant, temperature here I am assuming 298 Kelvin. I am not taking H plus as 1 molar. If I would have taken 1 molar and partial pressure of oxygen 1 molar, this would have been 0, but I am taking this as now a different value. So, it has a relation between the potential and the pH value, correct? That means, if the pH of the solution changes, your potential changes. The species which I am talking here is pH is related with H plus ion concentration. Now, do you see an instrument which is using this concept? Yes, pH meter which you use in your lab works on the concept. What you know, you take let us say sodium hydroxide, or you take HCl of unknown concentration, you stir it, put it under the electrode, you dip the electrode and you measure that potential, and that potential is what then basically is giving you the pH value, and you say okay, sodium hydroxide should be alkaline pH, HCl or H2SO4 is acidic pH. So, what actually that electrode does is it measures the potential which is because of the concentration of the proton which is present in the electrolyte, and that potential you do not see it in the front end. Basically, front end is directly calibrating the potential with pH, therefore, it gives a number 8 or number 9 or number 2. So, that electrode which we use to measure pH works on the function or works on the principle of Nernst equation, where the potential developed at an electrochemical interface is dependent on the concentration of the species involved into it, and also on the temperature at which the process takes place. So, from ideality, from standard conditions, I can't use it in my regular day-to-day activity. So, Nernst came up with this equation saying that the potential which is developed at that electrified interface is a function of the concentration and temperature. Now, what do I do further with this? I have made the pH meter. I know that the potential is dependent on the H plus concentration. Is there a possibility apart from the hydrogen electrode or the SHE electrode to have anything which I can use for practical applications? How many of you have gone through ECG measurements? Have you ever measured ECG? No? Hale and healthy. For precautionary, we have to do after 35, 40. So, we have gone through. What do they do in their ECG measurement? They will apply a gel and they use some kind of a connectors or electrodes which is kept. I use the word electrodes, some connectors, let us say, which has a metal tip at the top, and then it is connected to a recorder. What does that ECG graph look like? What does it measure? 22 times heartbeats up down. It is not the case, right? How does the ECG graph looks? Waveform. It gives some kind of a pulse waveform. I am not so special in drawing it. Let us say it gives something like that. So, what have you ever noticed what is in the y axis? Voltage. Why voltage? Where does voltage come from? No? Basically, it gives about the information of heart pumping in atria, ventricle, etc. based of voltage, because in your heart when the stimulus comes from the muscles, it is based on ion movement. There are potassium ions, sodium ions which involves in giving the trigger for the heart to contract now and pump up, and that ion is what giving you the electric potential, and that is what you measure in your ECG, and the tool which you use to measure that potential is nothing but a reference electrode which we use in electrochemistry, and that reference electrode we use is called as silver chloride reference electrode, which is analogous to what we use in standard hydrogen electrode. So, standard hydrogen electrode, how did you produce? You took a platinum wire, dip it into a solution containing acid, proton of 1 molar concentration, you purge that with hydrogen of 1 atmosphere, you maintain this particular reaction in reversibility and equilibrium, it gives me a potential 0. If I deviate any one of that, it will not give 0. So, I have to maintain that reaction at reversibility. So, if the same I can do it with a different compound of silver and silver chloride having an electrochemical interface, I will have a reference electrode made, and that will have its own value here. Typically based on certain concentration, it will be varying, let us say chloride concentration 207 millivolts. So, if I have to fabricate a reference electrode, I again need to use the concept of electrochemical reactions, maintaining it at reversibility and at equilibrium. I can have an electrode which gives me a single potential, and I can maintain this at single potential, then I can take it as a reference electrode for my applications. So, for electrochemical or corrosion experiments, standard hydrogen electrode is the primary reference electrode people often used, but of late, because of you have to use hydrogen gas or you have to use acids, people moved on to metal oxide or metal compound common ion electrodes, which would solve the same purpose. They are only with reference to that I am going to measure what is the potential developed at that interface. So, it is like I want to find out who is the tallest in this class. I will choose one person and keep it as safe as possible. With reference to him, I am going to order the other people. So, the function of your reference electrode is exactly the same, and the electrochemistry of reference electrode should be fixed at reversible conditions to give a unique potential. For example, if I see here, this is unique potential you cannot have in any other system, because it is for unique conditions, right. I said to make standard hydrogen electrode, I said I use a platinum wire in an acid which contains 1 molar concentration of an H plus ion. My question is, why did I use platinum? Why not, let us say, copper? Or can I use any other metal? So, you have to use for hydrogen electrode, when you dip it in an acid, the metal which you use should be a very good catalytic surface for this particular reaction which you talk about, and it should not react in that environment. It should be noble or immune in that environment. Can I use gold? So, for an hydrogen electrode, it is not mandatory to use only platinum, but most often platinum is preferred because of its catalytic activity for the hydrogen reaction, but you can use gold also, and it is not mandatory you need to use only HCl or perchloric acid. The requirement is only that the proton concentration should be 1 molar. Until you maintain this, you will be able to say that this is a standard hydrogen electrode. But if I have to use in my laboratory, you come to our lab, you will not see standard hydrogen electrode, you will see the secondary reference electrodes which we use to measure potentials. So, the cell or the electrode which is used to measure your heart rate is nothing but a silver chloride electrode. Okay. Where does it come from? It comes to measure that potential which is generated by the ion or charged species involved in your physiological conditions. Okay. Now, this is a very interesting thing to know. I said about a metal being exposed thermodynamically. I would like to see in an aqueous conditions, when does the metal corrode, when it does not corrode or remains as it is, or when it corrodes as an anionic species or a cationic species. This I can understand from the thermodynamical concept if I understand Poube diagram. Marcel Poube is a Belgian scientist who worked on this basically Poube diagram, and this was his dissertation or thesis for his PhD. You look into the web, you will find Atlas of Poube diagram. It is nothing but his PhD dissertation completely on understanding the metal reactivity, thermodynamic interpretation of corrosion process. So, what do we see here? The x axis is pH, the y axis is potential. What does it mean? In an aqueous media, based on your water ability, you will say talk about acid, neutral, base, and in the y axis it is based on the potential. The first thing when we talk about, we said that it is a metal water system. So, first I need to identify where water itself is stable. We all would have done in chemistry, the first in your school, that you can electrolyze water. You put 2 electrodes, you apply a certain potential or applied potential, you will see that one side you have hydrogen evolving, other side oxygen evolving. Basically, you are doing water splitting. Now, in conditions where you have, it is possible to identify where water remains as liquid, at what conditions it is evolving as hydrogen gas, and what conditions it is evolving as an oxygen gas. What is this line? This corresponds to reversible hydrogen line. So, anything below this in terms of potential or pH, it will be stable, water will be stable as hydrogen gas, and within the gray shaded region, water will be stable as water molecule. Above this region, you will see that this is oxygen reduction line, oxygen reduction reaction or oxygen reversible line, where you will see it is stable as oxygen gas. So, what I say, if I take a metal and I put it in an aqueous solution, based on what the metal does, it can be possible that the metal has the tendency to split up water. That means, metal will give electrons, one of the species is going to pick up that electrons. It could be proton or it could be the ORR, oxygen reduction reaction. So, the Poube diagram is basically a thermodynamical concept to show you what are the feasible regions for corrosion, and this is completely based on the Nernst equation as we saw in the potential. If you look at this particular equation, is it somewhere represented there? E equal to minus 0.059 into pH. Is that line available somewhere? What is this line? What is this equation for? This is the reversible hydrogen line. Is there a reversible hydrogen line there? This is the reversible hydrogen. At pH 0, potential is 0. At pH 14, this value is minus 0.829. So, what does it say? For this reversible line, It depends the potential and pH. It depends on the potential and pH. Within the border below which it is going to be as hydrogen, above that it is going to be water molecule. Same is the case for reversible oxygen line. This equation will more or less look like, I am not solving it here, but you can assume it is running parallel. So, is it dependent on pH and potential, or it is independent of pH? It is running parallel to the previous one. Reversible hydrogen line, reversible oxygen line, E will be equal to 1.23 minus 0.059 into pH. So, at 0 pH this is 1.23, at 14 pH this is 0.401. Based on these two, is there any device which gives us energy or can be used to produce energy in renewable science using this concept of electrochemical reaction? PEM fuel cells. Basically, fuel cells worked on this concept of one side you have hydrogen as a fuel, other type you have oxygen as a fuel. On an membrane electrode assembly, you will have oxygen being reduced on one side, hydrogen being oxidized. So, it should theoretically give me a potential of 1.23 volt. So, this is based on this particular concept. Now, where does the metal come in here? If I know where hydrogen is stable, water is stable and oxygen is stable, I should be talk about how metal plays. So, I will just give you a quick brief into it. It is a thermodynamic approach to corrosion reactions. It is nothing but the potential, which is again free energy, versus pH, because you are talking about water system. And if I assume this is my electrochemical reaction involved, this will be the Nernst equation for it, which says the potential is dependent on the concentration of the species involved in the reaction, and we assume that activity all to be is 1, and in general you will assume that if it is less than or greater than a certain amount of 10 to the power of minus 6, if I assume the ion is much lesser than this, then there is no corrosion or the metal is immune. Now, let us try to draw for aluminum. Are you aware of aluminum? What is the potential we saw for aluminum in EMF series? It is active or nobler? What is the value? Minus 1.67. So, this line is based on the E naught value. I am assuming the concentration of the solution is to be 1 molar. So, E will be equal to E naught, that is equal to minus 1.67. So, this line now is horizontal. What does it mean? It is independent of pH and dependent only on the potential value. So, wherever an electron is coming only in the equation, it is an electrochemical reaction, and only electron, it is going to be dependent only on the potential. So, in a Puber diagram, it should be an horizontal line. What does it separate? It separates between the metal and the metal ion. And the metal ion in this case is a cationic species. So, if I am well within this region, aluminum will like to stay as aluminum, but if I cross this, it will become Al3 plus. Now, this is one, and look at this one. I am talking about the equilibrium now. Metal can become a metal ion. It is also possible that metal can become a metal oxide. So, I am writing an electrochemical equilibrium reaction between a metal and metal oxide. So, what happens here? I have 6 H plus and 6 electron. So, this is dependent on both or independent of both? 6 H plus 6 electrons. It will be a slanting line in your Puber diagram. It depends on the pH as well as the potential. So, this allows me to draw the equilibrium. The red line is the equilibrium line for as we draw for oxygen reversible line, reversible oxygen line or reversible hydrogen line. This is a reversible line for metal and metal oxide. So, this gives me an idea about which boundary the metal would like to be as metal and which boundary it will become an oxide, right. The third one which you need to consider now is metal cation can also have an equilibrium with the metal oxide. Is it chemical or electrochemical reaction? Is there an electron flow? Al3 plus, Al3 plus. And you have only the proton involved here. That means it is a chemical reaction. You will use the concept of chemical equilibrium and you will try to find out the activity, and you can find out how it is related with respect to pH. So, basically this would be a vertical line in the Pooh-Bear diagram which separates between Al3 plus and oxide. The anything left towards us will be Al3 plus and the right towards will be oxide. We can discuss it while we are talking about tutorials. You can ask me questions why it is denoted in this way. So, in a Pooh-Bear diagram, if the reaction is chemical in nature and involves only H plus and no electrons, it is going to be a vertical line in the Pooh-Bear diagram which separates. So, first I said metal can become a metal cation. Metal cation can, or metal can have an equilibrium with metal oxide, and third I am talking about metal oxide being in equilibrium with the metal cation. There is also one more possibility which you can consider is the metal oxide as an anionic species. It dissolves as an anionic species, and in the right what you see here, it is again only H plus. So, it is a vertical line here which appears, which gives an equilibrium between metal oxide and metal cationic species. So, the dissolution of the metal in this case is cationic, in this case it is alkyonic, in this is anionic, and it is close to 13. That means, if I take aluminum oxide, dissolve it in sodium hydroxide where pH is somewhere between 13 to 14, it will dissolve as Al O2 minus in the anionic form. So, I do all the magic, remove all the overlapping lines, I get this as a Pooh-Bear diagram, metal and metal ion. So, here is metal, this is Al3 plus, and this line is basically between metal and metal oxide, and this vertical line is between the metal ion and metal oxide, cation and metal oxide and metal anionic species. So, based on this, what I can understand, within this boundary of potentials and pH, the yellow region, aluminum would love to stay as aluminum. Slightly any change of environment or potential, if it stays at this position, it will dissolve as Al3 plus. So, it is corroding as Al3 plus. In pH range of 3 to 12, if I am having somewhere the environment is lying in this potential, aluminum will always passivate, forming Al2O3, and if the pH changes by any means, you go to the pH of extra to the alkaline conditions, this oxide will slowly dissolve or dissolve into Al O2 minus. So, the Pooh-Bear diagram of this aluminum water system says me that, look, aluminum is immune in a very small window range. It is passive between the pH ranges of 3 to 13, and you can have aluminum dissolving in an acidic conditions at this potential ranges, and as a anionic species it dissolves again in the alkaline conditions. So, what do I say here? It is immune region. Since it is dissolving as a cationic species, dissolution is corrosion. Here it is again corrosion. The green region is the passive region. So, now I ask you a question. Can I electrodeposit aluminum from aqueous solution? Repeat the question. Can I electrodeposit aluminum from aqueous solution? You can electrodeposit. Why? Recall, this is your reversible hydrogen line. With this window, water remains water. If I take, for example, aluminum chloride in aqueous medium, I apply a potential, I have to apply somewhere, let us say minus 2 volt. You will have lot of hydrogen evolving rather than aluminum depositing. So, it is nearly impossible to deposit aluminum from aqueous medium. You have to use a non-aqueous medium in order to deposit aluminum. This is, yeah. Yeah, this one. Vertical line. This is dependent only on pH, independent of potential. Yeah, this one is independent of pH. From here, this is a redundant part which doesn't matter to me. Same way, this red line gives me a boundary between aluminum and aluminum oxide. So, I don't need to look at the boundary of aluminum oxide and aluminum metal. So, basically this gives me the immediate possibility where aluminum will become Al2O3. So, this slanting line is what I have drawn in the next case. I have removed the horizontal line here, and this will be the stability region where aluminum remains as metal. Just you cross this one, it will become oxide. So, the other one is a redundant thing which does not give me any meaning. So, therefore, I have erased the black line. So, this slanting line will be equilibrium line between or reversible line between aluminum and aluminum oxide, which is dependent on both pH and potential, right. Okay. I do not want to get into more. So, this is just what you use in the case of you can generate your Poubet diagram. Nowadays, you have softwares which allows you to plug in values and draw, but it is you have to understand only three possible things. One is a horizontal line, which means it is only reaction containing electron. It is independent of pH, Fe, Fe2 plus. Here Fe3 plus and Fe2O3, it is a vertical line. It depends only on the pH, independent of potential. And this slanting line is between Fe2 plus and Fe2O3. It is dependent on both pH and the potential. So, the Poubet diagram can be drawn for any metal system you name. If you take one, electrochemical equilibrium between metal and metal cation. Second, electrochemical equilibrium between or chemical equilibrium between metal oxide and metal. It will be an electrochemical equilibrium. Third, a chemical equilibrium between a metal oxide and metal ion. Fourth, the chemical equilibrium between a metal and its metal oxide and its anionic species. So, normally if what do I understand from this diagram? If I take aluminum oxide, put it in acid, it will dissolve, put it in base, it will dissolve. So, we call this as amphoteric oxides. Now, how do we use this for our research? That is what I want to show. So, my purpose is now to produce nanostructures using aluminum oxide concept, right. So, how do I produce nanostructures? I want to produce, let us say, metal nanowire or a metal oxide nanowires. So, what we started with is we use the concept of anodization of aluminum, which existed from 1936, and this became very important after 1995, where they found out if you can engineer these oxides into nanoporous structures, and then you can now use this as a template to put in metals or metal oxides. So, what we started with? We started with the pure aluminum, right. We electropolished it to get a very nice smooth surface. We anodized in a particular condition and solution. We got porous structure, and that pore in the first step is not ordered properly. So, we removed it again. Now, this removal you see oxide etching. We would have used a solution which is either pH base or pH at the acidic conditions. We used an etching conditions. We removed the base of only the oxide, and aluminum remains with these marks, and we drew or we again applied a potential to grow the oxide. It got into a ordered channel of nanoporous material. In conventional, what people used to do is, after this step, they will remove this blue aluminum. It will be only a template which will be open. This is a nanoporous alumina template, AAO template, over on which they will deposit a gold layer, which gives them the conductivity for further deposition of the system. But now we wanted to shortcut this path. What we did? We took it from here. We did not go for removal of aluminum. We created cracks in these bottom pores, which gives me the electrical conductivity. If that gives me the electrical conductivity, basically aluminum is contacted. Now, I can deposit whatever I want into the system. So, this is how we produced nanoporous alumina. Is it really porous? This is a cross sectional image. You see the barrier layer at the bottom. This is the channel at which it runs to a long distance. And if you look at the bottom of the pore, it is all closed in an hexagonal fashion. And looked at it, we did the barrier layer thinning to open up the closed pierce, you see that it is all opened, and we use simple electrochemical concept. What did we do? We took aluminum is the back plate, this is your grown alumina, and you have BLT done, that means your porous conditions are there. We put it in a copper chloride solution, aluminum dissolves, it is active, so it will dissolve, and then you have copper ions, the electrons are on the metal, the copper ions are in the solution reduce to form copper, and we deposit, and side by side you will have hydrogen evolution reaction. So, we can with a single step using galvanic displacement process, that aluminum is more activer than the copper ion in the solution. Aluminum will be the source of electron, and the copper ions can pick up this electron and deposit into the pores. We could able to achieve copper nanowires directly depositing inside the AO template without any post processing. So, what concepts we used here? We used the concept of Pube diagram, that if I have to dissolve an oxide, I need to identify what conditions I should work with. Second, I use the concept of a simple EMF theory to look at copper is more nobler than aluminum. If aluminum dissolves, it can give me the source of electrons, and copper ion can pick up those electrons to reduce as a metallic nanowire, and we could deposit nanowires into the channel of AO pores. This allows me to give me an idea about where I can use it as. Now, what I need to do, if I have to get these wires out, I have to identify the region where copper remains immune, but or copper becomes a copper oxide, but alumina should dissolve. Again, I will go back to the Pube diagram, identify at what conditions and potentials I can achieve it. So, this is one way of you use the Pube diagram for a research perspective. But from an engineering perspective, how do I use Pube diagram? You said the concept of galvanization of iron, and you said iron coated with zinc helps you to prevent iron from corrosion by cathodic protection. What does it do? Zinc sacrifices its electron. So, let us say this is the iron diagram. Iron is in this conditions of application, it is dissolving as Fe2 plus, you deposited zinc on it, you galvanized it, and now you are saying that iron is becoming immune, or iron is actually cathodically protected. What do you actually do when zinc is giving electron? What happens to the iron surface? Let us say this is your iron, and over and above you are coated with zinc. This is one scenario which you can think, or I have an iron structure and I have a zinc metal which is now electrically connected, and this is your environment. So, this guy becomes zinc 2 plus, and 2 electrons stay here, and the electrons get into the ion system, right. So, when electron gets into the system, what does it become, anodic or cathodic? So, when cathodic, its ion is becoming more and more cathodic, the potential moves from this slowly to the immune region. So, this is where we use the Pube diagram for engineering in terms of protection for cathodic protection. We know at what potentials you can apply to bring the iron from corrosion system to an immune system. Is there any other protection method which I can get from Pube diagram? Passivation. So, I can do anodic protection if I know the conditions. Instead of having iron Fe2 plus here, I can shift the potential or the conditions of pH to bring it into a passive layer. So, that is called as to anodic protection by applied potential or by chemical passivation. So, Pube diagram gives me an idea about the stability of a particular system, thermodynamical stability. Iron remains immune in the gray region, in Fe2 plus in the acidic, in these potential ranges. So, I can use this concept to bring it as cathodic protection or move it towards anodic protection. Pube diagram has an issue. What issue is that? If it says only that it corrodes here, it corrodes at this region, but it does not say how fast or how slow it corrodes, because thermodynamics always gives you only the feasibility of the process. It does not say what path, how fast, as professor pointed out. It says only the water will move from the top to the bottom, but how fast and slow depends on the path and the pipeline, the kinetics rate determining aspect. So the thermodynamical aspect is what? It's only the feasibility of the reaction. The kinetics, you can't get information from the Pouget diagram. Of course, there are a lot of assumptions made in the Pouget diagram. First assumption is you assumed all the activity of the active elements are 1, but need not be. If you have multiple systems, its predominant system is considered to be 1. If you have multiple systems, the activity need not be 1 for each. So that becomes a deviation, and of course it works on the, as I did the calculation, it depends on your delta G value which you need to get from the chemical data. So this is how you use Pouget diagram, or you interpret Pouget diagram for identifying the corrosion behavior of a metal. If you are starting with a new metal system, for example, you can easily look into a Pouget diagram and identify what can be my environment to keep it as a passive layer or a passive system. What can be the environment at which I can have it as an immune system. So this freedom Pouget diagram gives us much more from the simple concept of thermodynamics, right. So what did I say? To summarize, when I talk about thermodynamics in aqueous systems, we talk about potential. I said you that the potential developed is because of an electrified interface. I said difference between a single electrode and a mixed electrode, reversible condition and irreversible condition. Corrosion is an irreversible process. My EMF series will not help me very much. So Nernst equation is what I need to use to fix the potential with respect to concentration of species and temperature, and that gives again E only. Then you get the Pouget diagram as the base to read corrosion for metal water system, right. That's, and thermodynamics is only the feasibility. You can't say it corrodes at 10 rate or 20 rate. It gives only that it will corrode or not corrode. What gives me the information about the rate? Kinetics. So in the case of electrochemistry, what parameter would be give me the rate information? In electrochemistry, what parameter will give me the kinetic information? Potential gives you your feasibility. So what will give you your kinetic information? Current or current density. So the next we would look ahead is with respect to electrode kinetics. Glance into it. Assume this is the reaction. Zinc is dissolved in HCl. We all know after a certain period of time, the turning of zinc which I have put it in the test tube will be gone. You will not be able to see it. This is the overall reaction. This is solid, aqueous, solid and gaseous phase. On the same surface you will see hydrogen evolving, and this particular overall reaction can be divided into half cells or partial cells. If I consider this, zinc is becoming zinc 2 plus and 2 electron, and this electron is now picked up by the proton which is present, forming 2H plus 2 electron. So for an overall reaction, you can divide that into multiple partial reactions. How many partials we have divided here? Zinc 2 plus 2 electrons, 2H plus 2 electrons giving H2. Now, assume that I have an electrochemical reaction. This reaction is in reversible reaction and it is at equilibrium. Let us say there is a forward rate Kf and there is a reverse rate Kr, right, and it is at dynamic equilibrium. What do I mean by dynamic equilibrium? If I have, for example, 10 metal ions is becoming 10 metal, and the same 10 metal is becoming a 10 metal ion. So the reaction is reversible and equilibrium. Dynamic equilibrium means, then what is this rate? Is it 0 or it has some finite value? Is this reaction rate 0 or it has a finite value? I am throwing a ball to you, you are throwing back to me. Is there an action going on, keep on going, or nothing is happening? Right? At dynamic equilibrium, this has a definite value, and that is basically, if I write Kf, you said you won't accepted that the rate of the reaction is given by current, and here I am going this to as current density in small because I am normalizing to the area. I name it as C because this is a cathodic reaction. Here I am current density is I and this is an anodic reaction. So, I am giving me a subscript A, here I am giving a subscript C. By convention this is negative and by convention the anodic current density is positive. This is called as partial anodic current density and this is called as partial cathodic current density. Now, I said this is a dynamic equilibrium. So, my Kf should be equal to Kr is not equal to 0, but it has a finite value, let us say that is x, right. So, in that case my minus Ic is equal to plus Ia is equal to a parameter which is called as exchange current density. Have you heard this? What does it mean? What does it mean? Who said yes? Equilibrium rate of forward and backward reaction is exchange current density. I normally give an analogy for this. What car do you like? You are given a Land Rover after the Gian course, right? You are going from here to Karaikudi. First thing what will you do once you sit into the car? Open the door, you sit in, you switch on, probably an automatic on off, you do not need to put the key, you will press the button, engine is on. Now you press the accelerator. What happens to the car? It is not an auto gear. It is a manual gear, Land Rover with manual gear. You just switch on, engine is on, you press the accelerator. What happens to the engine? There will be a screen which gives you the RPM. So, only the engine RPM changes. So, for an electrochemical reaction which is in synonymous case now, it is called as an idling rate for the car. The engine is only idling, the car does not move. This particular exchange current density is equal to that idling rate. Only engine is on, the reaction is in reversible condition, it does not move from that position. So, this is what defined by exchange current density as equilibrium rate for this redox reaction or forward or reversible reaction. So, this I naught is equal to your car which you switched on, you are not engaged gear, you have done nothing, you are just pressing the gear. You have an ambassador, right. I have a very old ambassador, assume you have the latest Land Rover. The accelerator effect is different for these two. I am pressing too much, what engine gives only to 20 RPM, but your case it press it gives you 40,000 RPM. What is the difference between these two? So, it is easy, it is fast in the case of your Land Rover, but ambassador it is very sluggish. So, for an electrochemical reaction under equilibrium, reversible equilibrium conditions, I naught talks about the fastness or the sluggishness of the reaction, right. If the value is lesser, it is sluggish, if the value is higher, it is fast. So, the Land Rover is more faster in terms of the idling rate, but the ambassador is slower in terms of idling rate. So, the I naught gives you an hint or idea about this reversible reaction, how fast or how sluggish it is. Now, if this is a reversible reaction at equilibrium, it should have one value of potential H plus, remember of 2 H plus 2 electrons forward backward H2, you said the value is 0. What is that value? So, this value is your E naught of this particular reaction. So, in equilibrium reversible conditions, you have two parameters which determines or gives the value of it is basically E naught and I naught of that particular reaction, right. Now, assume that this zinc, the electron which is given by the zinc is not consumed by the proton. What would have been? This probable reaction would have been in reversibility. So, this would have had an I naught value, E naught value, this would have had an I naught value. So, for that partial of zinc, I would have had an I naught and E naught value, and that value and I naught and E naught will depend on what is the electrode, what is the area of the electrode, what is the electrolyte, and how does it relate. That we will see in the next slide. So, I naught is the exchange current density of the system. It is not 0, it is a finite value. It talks about fastness and sluggishness of an electrochemical reaction at reversibility, and I naught is related, you can consider as I also here because area can come down, N F Farad, number of electrons, area of electrode, if it is capital I, area is correct, rate of the reaction which we do not borrow, but it talks about the concentration of the species involved in the reaction. For example, if I assume proton, right. So, I naught of this reaction will depend on the concentration of H plus and the partial pressure of H plus, and also the area and also what the solution is. So, the I naught is unique for a particular electrochemical reaction on a particular electrode surface in a particular electrochemical medium or an electrolyte. It cannot have the same value for all cases. So, I naught, for example, on hydrogen, this reversible reaction on platinum in sulfuric acid will be different on zinc in sulfuric acid. You should understand this I naught value is dependent on whether the car is Ambassador or Land Rover. If it is I naught on platinum, hydrogen evolution reaction is much easier because of its catalytic activity. It will show very fastness in the reaction, but on zinc surface it is sluggish. Okay. So, this I naught will again depend on what is the concentration of the species involved. This alpha, which is called as the symmetry factor, or it is called as a symmetry factor. I will explain it when we go further. Normally, you can consider to be 0.5 in both cases. So, kinetics is talked in terms of current. Current, when I normalize it to area, I can make it as current density. For an electrochemical reaction or a corrosion process, you can divide that into multiple partial reactions, which then you can relate it with respect to one, basically a partial anodic reaction and a partial cathodic reaction. At dynamic equilibrium, if an electrochemical reaction is reversible, the rate at dynamic equilibrium is given by I naught value, and it has a potential which is E naught, right. Now, I am talking about I naught. So, I will assume this is my simplest electrochemical reaction which I am talking, that is reversible hydrogen line. I know if everything is in standard conditions, this is equal to 0 volt, and that is with respect to this is the value of this. And now, when I consider this is the forward direction, which is reduction, this is your backward reduction, this IC is equal to plus partial IA is equal to an I naught of this reaction happening on the surface of what metal I am talking. If I am talking platinum, this will be on the platinum surface, and also on what electrolyte I use, right. So, this I naught value of this depends on what metal surface it reacts, that is on the electrode composition, the purity, the surface roughness, and also what is the electrolyte I use. I can produce this by using HCl, I can also produce this by using HClO4, I can also produce this by H2SO4. So, for each electrolyte, your I naught on the same platinum surface will not be the same, it will vary, right. So, I naught, in other words, you have to be very specific for what reaction I am talking, on what surface I am talking, and what medium I am talking, and what is the purity or what is the temperature I am talking. This will all change your I naught value. And I naught value is what? Just you have switched on the engine, engine is just hot now. The car is not moved anywhere, the reaction is in reversibility, or redox reaction is in equilibrium, right. In corrosion systems, I naught is measured from your potentiodynamic polarization curve, where you take back the Tafel extrapolation to the E0 value. You need to know what is the electrochemical reactions associated with it. For complex systems, you can't find out. For simple systems, you can find out by extrapolating your Tafel line to the E0 values. Without polarization, you can't. It is basically I0 is what? It is when your reaction is at equilibrium. We will talk about it when we talk. When I disturb this fellow from equilibrium, I disturb it by application of certain external energy, and that is what we call it as drawing a certain amount of current or pushing in a certain amount of current by application of potential. Then you need to come back to that potential to identify the I0, E0 and I0. But you can't, once your system, I will explain you when we talk about zinc reaction, I will say where I0 and E0 comes into picture and how you identify the corrosion rate of the metal. That is your mixed potential theory or Evans diagram. We will stop here and we will see the remaining in the 2 o'clock.